Let's now talk about continuous probability distributions. Among the well-known continuous probability distributions are the Gaussian, which is generally called the normal distribution, 2, the uniform distribution, 3, the exponential distribution, the Cauchy distribution, and so on. Let us now talk about the continuous probability distributions. Some of the famous continuous distributions are the Gaussian, which is called normal distribution also. We call the uniform distribution, exponential distribution, Cauchy distribution, and several others which come in the context of communication engineering. Specifically, we will talk about the normal distribution. Let X follow a normal distribution with mean mu and variance sigma squared. Suppose you know in advance the mean of the distribution and the variance, and you know the random variable is following the normal distribution. The probability density is given by f of x is equal to 1 by sigma root 2 pi, so this is standard deviation, into e power minus half x minus mean by standard deviation whole squared. And the range of x is the full range, minus infinity to plus infinity. If you actually plot this density function, you will find that it is a perfectly symmetrical distribution. It's called the bell-shaped function. This is the Gaussian density. The total area on the density is 1. So, integral minus infinity infinity f of x dx is perfectly equal to 1. Now, you can see that maximum probabilities are concentrated somewhere in that band, and as you go towards the end, the tail portions contribute very less probabilities. So there are some interesting points to be discussed. So let's look into that. Suppose you take the Gaussian density, this is the mean. Because of symmetry, it will be there. Suppose you take 2 points to the right and to the left of the mean, mean plus 1 standard deviation, mean minus 1 standard deviation. If you look at that probability, in fact, specifically, the mean to mean plus standard deviation will be 0.3413. The same thing will be here also, 0.3413. Therefore, probability that x lies between mean minus standard deviation and mean plus standard deviation is 0.3413 into 2. So, this will be 0.6826. So, that means nearly 68% of the total probability is concentrated in this band between mean minus standard deviation to mean plus standard deviation. Similarly, one can remember two standard deviation results. It's about 0.945. When it comes to 3 standard deviations, it's almost 100%. So these are significant results as far as probability distributions are concerned. As long as the distribution is normal for any mean and standard deviation, these are hard facts. So we can remember these things as standard. Now, generally it is very difficult to work with a random variable which is normally distributed with a non-zero mean and variance not equal to 1. So we'll introduce a new variable z and we'll try to modify the given normal distribution into a new normal distribution with much simpler properties. So I'm going to introduce to you the standard normal distribution now. Now let us first begin with a random variable x that is normally distributed with mean, mu and variance sigma squared. Now the density function of this, as we have already seen, is 1 by sigma root 2 pi into e power minus half x minus mean by standard deviation whole squared. Of course, the range is minus infinity to plus infinity. Now introduce z is equal to x minus mean by standard deviation. This z is called the standard normal variate. Okay. Now, when you find the mean of z, it is nothing but expectation of z, which is expectation of x minus mean by standard deviation. And using the properties of expectation, this is 1 by sigma into expectation of x minus expectation of mu. All of us know expectation of x is mean and expectation of mean is mean itself. So what you find is the mean of z will be 0. Remember, the mean of x is mu, but the mean of z is always 0. Similarly, when you take the variance of z, it will be nothing but expectation of z minus mean of z whole squared. But mean of z is already 0. So this is nothing but expectation of z squared. And if you actually work out, this comes out to 1. You will have to do simple expectation calculations. So what I want to tell you is mean of z is 0 and the variance of z is always equal to 1. Therefore, z follows a normal distribution with mean 0 and variance 1. If that is the case, the density function for z will be f of z is equal to 1 by root 2 pi e power minus half z squared. So please compare the density function of x, which looks like that, and compare it with the density function of z, which is highly simplified just because the mean is 0 and the variance is 1. Now if you draw the density function of z, it will also be Gaussian bell-shaped. But observe one thing clearly, the mean position is definitely 0, unlike the previous case where the mean was mu, a non-zero value. And z is equal to 1 corresponds to, this corresponds to mean plus standard deviation. So this will be 0.3413. This is z is equal to minus 1. So this will be another 0.3413. So if you remember the previous plot, we had the random variable x which was Gaussian distributed. The mean was mu. This point was x plus, rather mean plus 1 standard deviation. This was mean minus 1 standard deviation. But if you convert it to the standard variable, this, the mean position becomes 0. This becomes z is equal to what? Z is equal to minus 1. It is in fact with the help of this standard normal variate that normal distribution tables have been constructed. So now let's look into some illustrations based on the normal distribution.